This is the last video for homework for Chapter 7 in Statistics. In this case, we're going to look at the chi-square distribution. This term, written here sort of phonetically, is usually written in Greek as chi. It's pronounced chi, as in kite without the TE on the end of it. So it's a long I, chi. That's called chi-square distribution, and it has to do with computing the variance. Everything we looked for before was the mean. You wanted the average value. But what if you want the variance? Why would you want the variance? Well, say you have a factory where you make nuts and bolts. You don't want those dimensions to vary. You want that variance to be very small so that when you're done, the pieces parts will more or less fit together. So sometimes you look at the variance. Like with the t-distribution, this chi-square distribution has a group of curves. These curves, though, are not anywhere near bell-shaped, and they are not symmetric. Like the t-distribution, they depend on the degrees of freedom, and the degree of freedom, again, is the sample size minus 1. Here they use k when they should have written df, but when you take things that other people did, you really can't complain too much about them. I couldn't graph these chi-square distributions, so I had to take curves from the internet. Anyway, here are some chi distributions. You see, as the degrees of freedom increase, these curves look, well, they kind of smush out and look a little more symmetric, but hardly. They're not symmetric. And you only are concerned from here up, nothing negative. Remember that the variance was the standard deviation squared. Because it's squared, it can never be negative. So you're only worried about values from 0 up to positive infinity. Now, even though there's not a bell-shaped or even a symmetric curve, the same ideas are going to apply. The confidence level is going to be related to the area in percentage under the curve. Remember, when you had the bell-shaped curve or even a symmetric curve such as the t-distribution curve, for those symmetric curves, you had a certain area under here, say 90%. That means 10% of the area under the curve is rejected. You divide that by 2 and you get 5%, right? And so this 5% rejected area is in two tails, a right tail and a left tail, and they're the same, 5% over here, 5% over here. Now let's look at one of these chi-square distribution curves. Say we want to reject, let me get the pen. So the rejected area is going to be 5%. Half of that is 0.025. That's because we want, 99% confidence level. Okay, so we're going to reject this much. Each tail is going to reflect that much area under the curve. Well, here the curve's all very close to the origin, so you have to go, or to the x-axis, you have to go way out here to get this 0.025, or you could say 2.5% of the total area under the curve. On this side, on the left-hand side, the curve's very steep, so you don't have to go very far because it's very high. The value is much higher over here. So both of these areas are 2.5% each, but you can see there is not a lot of symmetry. Right? Before, when you found a z alpha over 2 or a t alpha, then minus that value would give you the edge of the left tail. Here, you're going to have one value for the right, so that's chi, and we'll put that right here. And over here, you're going to have another value. They are not going to be the opposite of each other. Well, they couldn't be anyway because this thing has to be totally positive. There's a procedure on how to find them. So here's the idea again. You're looking at the area under the curve. If you have a 90% confidence, area under the curve, then you're going to reject 10% of the area under the curve. If you want a 95% confidence level, then you're going to reject 5% of the area under the curve. The rejected area is going to be contained in tails. Each tail will contain half of the rejected area. So everything's the same up to now, but because of the lack of symmetry in this chi-square curve, you have to find different values for the edges. So this is what's being rejected on this side. You call that value chi and then subscript right. Here is the value rejected on this side, that's chi left, and this isn't x, these are really supposed to be chi's. There is a big confusion in the chi distribution concerning alpha. Look at this graph right here. They say alpha is 0.05, and then down here they say alpha equals 0.025. They're very free with the letter alpha, so be careful of that. I'm going to show you first the equation for the interval. Now remember that for these chi-square distributions we're looking at variance, so we want to find out the variance for the population. Right. S squared would be the variance for that sample that we measured. N minus 1, N is the size of the sample, so everything's fine up to here. But now you're going to divide by chi-squared for the right and chi-squared for the left. Look at the confidence intervals for the t-distribution just so you can see the difference. In this case, we're looking for the mean, the population average. Right. So we use the average for the samples. That makes sense. And now we have these t alpha over 2 values or z alpha over 2 values, and they're the same in both sides of the equation. And the chi-square distribution for variance, they aren't the same. There's a left value and a right value. Here's the procedure for finding the chi-square for the right and chi-square for the left. For chi-square for the right, you compute a value and call it alpha by subtracting the confidence level in decimal from 1 and dividing by 2. That's very similar to what we've done before. So if you wanted a 95% confidence level, you'll go 1 minus 0.9, which would give you 0.10, right? And you divide that by 2, so then your alpha would be half of that, which would be 0.05. Then you go to table G and appendix C, and you find chi-squared right. This is just, it won't tell you that, it'll just say chi-squared, because you look for the alpha value, and remember you had so many degrees of freedom, and that would be the rows. Right. Now you want to find the other one, chi-squared for the left. You compute another value, that should just say value, and you also call it alpha. Again, they use alpha, they make good use of alpha. Boy, they use it every place they can. So to do that, you subtract the right alpha from 1. So here's my alpha from the left, which should be subscripted if they did things right. Okay, you would take this value and subtract it from 1. So you've got 1 minus a 0.05. Okay, so it gives me 0.95. Now go back to appendix G, or table G and appendix C, and you will find the other value. Remember, you have the same degrees of freedom. Here's an example for 9 degrees of freedom. So 9 degrees of freedom meant you had sample size of 10. You want a confidence level of 95%. So you write the 95% as a decimal and you subtract it from 1, divided by 2, and you end up with alpha, this is for the right, equals 0.025. Fine. Then you go to table G, and for 9 degrees of freedom and an alpha of 0.025, you find that the chi-square for the right is 19.023. Now you want to find the one on the other side, chi-squared for the left. You take, let me get a pencil, you take this number and you subtract it from 1, and this is what you get, 0.975. You go back to table G, and for 9 degrees of freedom and this value for alpha, you find chi-squared for the left, which is 2.7. Those are your two values. Now you can use those values to compute the confidence interval for the variance for the entire population. So here's the equation we're going to plug into. We just did the one for 95% confidence level and 9 degrees of freedom, so we know those values. Here they are, 19.023 and the 2.7. Okay, so n minus 1, of course, is 9. That's 10 minus 1. And because we're given that the standard deviation for the sample is 23, put the 23 there and square it and work out the arithmetic. You find that with 95% confidence, you could say that the variance for the population lies between 250.28 and 1763.33. And now you should be able to do the homework. For the chi-square distribution, what's an example of a situation where variance would need to be controlled? Think of some manufacturing case where you have things that have to fit together. Now use appendix G and find values for chi-square right and chi-square left for sample size of 25. So your degrees of freedom would be 24. You want a confidence level of 90%. Okay, so you have to work out the procedure for chi-square of the right, and that involves 1 minus the 0.90 divided by 2. That will give you your alpha for the right. And then when you want the alpha for the left, you have to take 1 minus alpha for the right, and that gives you the alpha for the left. Go back, same degrees of freedom for both cases. Then you need to write the equation. I've just written it here. You can find it anywhere and copy it. So you know the equation that you're going to be plugging into. And then you can work out a sample problem. So here's a sample of 101 patients. That means your degrees of freedom will be 100. And you know the standard deviation for this sample is 47 minutes. What's the variance for the sample? Okay, this is a little tricky question. The standard deviation is, the standard deviation is 47. Fine. The variance is 47 squared. Actually, I should have used S. I'm sorry. S. And then the standard deviation is S squared. Now go to table G, and for 9 degrees of freedom, 100 degrees of freedom and a confidence level of 95%, find the chi-square right and the chi-square left. You know, I drew the first graph. On the first graph at the beginning of this lecture, I just wrote chi and I didn't write chi-squared. It really is chi-squared. You don't have to square anything. You're given that value. Okay? And then go ahead and compute the confidence interval for the variance of the time waiting in the emergency room.